It's my pleasure to introduce Boquan.
Yeah,
Or Owen.
that's good.
Chen, who we're very lucky to have with us because he just happens to be in the country at Cambridge, right, for a conference. So he's working currently with Janssen Ting in ANU and Stronglow in Australia. And I think you did your PhD in Wisconsin, is it with Elaine?
No, that's my undergrad master's.
Undergrad, yeah, sorry.
Yeah, PhD at University of Sydney.
Sydney, yeah. Before joining the group at ANU. So I think he's really an expert in chemical evolution and Milky Way. And I'm really excited to hear more about this, especially the alpha heteroids.
Nice. Thank you for your introduction. Hi, everyone. I'm Boquan Chen, or Irvin, from ANU. So today we'll talk about two things. So the first thing is the alpha to iron rise. So in the proton Milky Way, and the second thing is the alpha to iron bimodality that we see in this, and has perplexed astronomers for decades. So the first part of the presentation is going to be an introduction to chemical evolution model. What is chemical evolution model? What we're trying to do here. In summary, it's a model that tracks the temporal and sometimes spatial changes in the chemical composition of the galaxy, the whole galaxy we're trying to keep track of. Then I guess we have some simple questions here. Where do the chemicals come from? Anyone? Stars. Stars, yeah, exactly. So when you have stars, right, to make metals, of course. Then what forms stars? Cold dense gas, right? So we need to have cold gas as well. And the last thing here, so what form does newly released metal take? Anyone? Warm gas, right? So ionized gas. So that's basically all. We have three ingredients we need minimum for model here. We have cold gas, stars, and warm gas. And since stars are the most important ingredient because to make all the metals, we're going to dig into how we're going to use the stars, right? Because based on different kind of simulations, stars can mean very different things. So the first thing we need to do is actually to form stars. We form the stars in our model using the law. In case you're not familiar, it's the law that relates on the y-axis. On the x-axis here, this is the gas density, and the y-axis here is the star formation density. So these two actually related by Kanaka-Schmidt law. So once we know the density of the gas in our model, we can actually calculate how many newly formed stars we're going to have. And once you have the stars, we're going to distribute them based on their progenitor mass, right? And this is just, you can pick your favorite IMF here. I think people working on external galaxy like the Shabrar, and for us, we use the Salpeter or after we have the progenitor mass, where we can then record metallicity. Because once we form stars, we know exactly what the metallicity of the gas is. So we can then use the isochrone to actually calculate the maximum age, i.e. the lifetime of stars, right? So for all this model, we have metallicity, we have the mass, then we can calculate the age. Then we're going to have star evolution, right? Because stars need to die to give us the metal. So there are three channels, major channels in our model that we keep track of. So the first one is 4 collapse supernova, and they roughly come from stars with roughly more than 8 solar masses. There's a small metallicity dependence, but roughly larger than 8 solar mass. And the second channel that takes slightly longer is the HB stars. So these come from stars with 0.9 to 8 solar masses. They take from 10 year to 50 million years to die, so they cover a huge amount within the stellar progenitor mass range. And the last one is Taiwan supernova. These have the longest delay timescales because they need to die first, and then from the white dwarf, we're going to form the Taiwan supernova. And in case you're interested to know what the views actually look like, this is an example of the views from Type 2 supernovae. So you can see here on the top, we have the progenitor mass from 13 solar mass all the way to 40. And then we have the energy. Then we also have the mass remnant. So you can see for 13 solar mass, or after it dies, you have a remnant with 1.57 solar mass. And then we have all these elements. We have the mass that's supposed to come out from each star. So by using these tables for each nucleosynthesis channel, we can calculate how much metal is coming out from each nucleosynthesis event. So this is the astronomers' periodic table, in case you haven't seen this before. So again, each box here, we have one element, and within each box from left to right actually shows the accumulation of that element in mass over time. So there's actually a vertical dashed line here that shows the solar component. So this is where how much, so for example, here for barium, this is how much barium the sun has. So of course, it goes beyond that. So you can see that from different elements, they have different preferred channels. And depending on what time you're looking at, the channel producing the element can be very, very different, right? So we care about, so for this talk, we mostly care about iron and magnesium. So if you look at iron here in the beginning, we have more blue. So those are cold-collide supernovae. They are massive stars. And then very soon, we're going to switch over to type 1a supernovae, and they're going to produce the majority of irons we're going to see. And same thing for magnesium. Yeah, right here. So for magnesium, the picture is simpler, right? It's mostly dominated by blue, the massive stars. And then later on, we're going to have some contribution from AGB stars. So for the disk, you can roughly say that iron is mostly produced by type 1a and magnesium produced by massive stars, cold-collide supernovae. But just keep in mind that early on, when it's very, very metal poor, for example, for the proto Milky Way, we have metallicity -2, -1.5. The contribution from cold-collide supernovae is higher for iron. And just to give you some idea of how much each element is actually produced from each event, I have some numbers here. So the first one, we have a 9 solar mass star, which has a lifetime of 35 million years. So it dies very, very quickly. So in our model, this is roughly just 1 to 2 time step, right? It doesn't live very long. But it only releases 0.06 solar mass of magnesium and 0.005 solar mass iron. The number changes a little bit based on metallicity, but it's roughly the same number. Same thing, but then if you look at the lower mass star, right, 3 solar mass star that has a lifetime of 350 million years, it will give us a 0.8 solar mass white dwarf. And then from the white dwarf, once we reach Chandrasekhar mass, we're going to have 0.7 solar mass of iron. So you can see that in absolute amount here for each star, the type 1a is going to produce much more iron than magnesium and iron from a massive star. And of course, based on initial mass function, we're going to have a lot more lower mass stars than massive stars, right? So just keep that in mind because later on it's going to be important. Just to caution, so even if 2 elements are produced from the same channel, so we're looking at just AGB yields here. So this is the ratio between barium to yttrium on the y-axis. It can change based on the metallicity. So if you pay attention to the blue line and the orange line here, they correspond to stars with progenitor mass 2 and 3 solar mass. And you can see that the barium to yttrium ratio started high, but then after which metallicity -1, it rapidly drops, right? So even for the same nuclear synthesis channel, we're going to have very different ratios depending on what metallicity you're looking at. Yeah.
So is that how much is in stars?
How much?
So then you have the ratio there. So that's the ratio in stars.
Exactly. Well, yeah. So that's the ratio of the in the gas that's being released by the star. Yeah, when it dies. Yes.
Okay.
Yeah. So if you so same thing for cold-collide supernovae. If it dies, you can see that based on the number we had here, the magnesium to iron ratio is going to be much higher. Yeah, just for the yields.
Okay, so that's the output.
Yes, yes. And that's sort of the limit, right? For example, if you have pure cold-collide supernovae, then the mass ratio between magnesium and iron sets the upper limit for that ratio. Right, so it's just a summary. How do we do star formation and metal production? We calculate the mass based on Kanaka-Schmidt law. We distribute the mass based on IMF. We record the metallicity. We calculate the lifetime based on isochrome. And then we're going to calculate the elements based on nuclear synthesis tables. So these are the basic ingredients that we need, like at minimum, to run this model, to generate the metals and then to keep track of them. So you can see everything's very simple. You learn this in Astronomy 101, but when you put everything together, things get kind of complicated. So we've done the stars here already. So after the gas is produced, released from the stars, right? So we have nuclear synthesis. All the gas released as warm gas. And so the warm gas reservoir in our galaxy can be replenished by infall, which is surrounding gas around the galaxy. And then the warm gas can cool into cold gas. And then when cold gas gets condensed, you can form new stars. And basically, we run this recycling of materials in our model over and over again for however long you want, and then we can generate a chemical evolution track from the galaxy. Great. So now we're gonna do something with this chemical evolution model. Yeah, question?
The pollution phase.
Yes.
How do you control kind of how far the pollution goes, or do you assume that all the gas gets enriched equally, or what happens with that phase?
That's a good question. So in our model, the size of the bin is 250 parsecs, and most of the pollution only happens locally. Yeah. So 1% of the nuclear synthesis yields will be polluting the surrounding ISM within the zone. But of course, we have for later on, we're going to have multiple boxes together representing different radii of a galaxy. Then there is also gas flow present in the disk that can transport some of the polluted gas around.
How about things kind of outflows that kind of pull back into the galaxy? Do you worry about those at all, or are they not big enough for the deal? Or
yes. So if you believe we have a galactic fountain that can actually disperse the gas to a larger radii. But later on in the multi-zone model, for now, we're still constraining the gas locally and just relying on gas transfer within the disk to do that. Yeah, but it's a topic that's been brought up many times, so it's interesting to explore as well. Question? Perfect.
Yeah, what is really contained in this pollution? Is this like cold stellar winds?
Yes. So when it's polluting, it's going to take the form of cold gas. It's not going to be warm gas.
So no supernova ejector.
It's part of the supernova ejector. So when the gas is released from a supernova, 1% of the gas is going to take the form of cold gas and pollute the surrounding ISM. So that gas can be reincorporated into a for a new round of star formation immediately in the next time step.
But the ejector is quite hot.
It's quite what?
The ejector is quite warm.
Yeah. So 99% will be going into the warm gas. Yes.
Okay.
Yeah. A guy asked it, so hopefully it's clear. So actually, you can also change. So not all of the ejector will be coming back, right? So some of the ejector will be very, very hot. It will take them more than 10 billion years to come back. Effectively, they're lost. So typically 10 to 15% in our model is lost forever to the model, and the remaining will go to warm gas that cools over time. In case you also wonder about the cooling time scale, the cooling time scale is about 1 billion year. So it take, for most of the gas will take like much longer to cool. Great. Any more questions on the model? Yes.
So this looks like a pretty simple model in terms of how you described it so far, and there are some bits here like synthesis that you talked about.
Yeah.
But for the other parts of this, how much of this is like tuned based on simulations versus like a relatively simple analytic model where you kind of do the processing of gas?
So it depends. So for the alpha to iron increase, we only have one zone, and we have very little observational evidence. We know roughly how much it go up, but we don't really know the ages of the stars, so we don't really know the time scale of the event. So we basically we pick the parameter values based on literature values that people have measured from external galaxies or nearby groups or within the Milky Way. Then we try to stick to those values as much as we can, and then for the rest of the value, we can set them as free parameters, and then we can run the model many, many times to generate a parameter distribution. Yeah.
Let's say for like cooling feedback, inflow, pollution, star formation.
Yeah.
Those bits, I mean, are these coming? I mean, is it? I've seen like other models that are basically kind of a very simple analytic model versus taking something more from simulations.
Yes. Let me just quickly jump ahead a little bit. Right. Oh, this is me. Okay, I'll show you a table later that has a parameter value. Then we can talk about that as well.
Nuclear synthesis, right?
Yeah. What do you mean by nuclear synthesis?
That's set by the yield, isn't it? So I think there's no parameters there.
Yeah, it's purely determined by the yields.
Part, yes, but let's say the way that feedback affects gas.
Yes.
How is that kind of entering your model?
Okay, so
what are the assumptions behind that in your model?
Yeah, so the feedback is primarily coming from supernovae. So when you have a supernova event, we excite or ionize some of the cold gas into warm gas. And that's determined by a mass loading factor from the literature value. So I think it's several times, up to 10 times, I think, from ISM simulations. So yeah, we take that from literature value as well.
I think for these kind of models, the mass loading factor is a parameter, isn't it? It's often
Yes.
vary that as well.
Yes.
Yeah.
But I think for the mass loading factor, it doesn't affect the chemical evolution as much, because when you talk about chemical abundance ratio, it's the ratio, right? So when you have a mass loading factor, you remove everything altogether. Yes, it does. So yes, it will affect your stellar distribution, but doesn't necessarily affect your chemical abundance. Yeah. Perfect. We're just going to look at the alpha to iron rise observing the proton Milky Way. So all of this started from this paper by Belokurov and Krasov early last year. So essentially, if you look at, sorry, we have a lot of lines here. Y-axis here shows the tangential velocity of stars in the Milky Way observed from Gaia data, cross-matched with apogee. And the color lines actually show the same trend from simulated galaxies. So you can see here on the left here, from 13 gigayears ago to present day, the tangential velocity actually sharply increases sometime when the disk forms. And you can do the same thing with metallicity, since we don't have very accurate ages from these stars. So you can see that after we reach metallicity minus 1.5, the tangential velocity sharply increases, right? So this is interpreted as the formation of the disk. So when the disk form, all the gas clouds are coming in, the angular momentum is incorporated into the disk. So the star started spinning. Then we have the disk. But the byproduct of this paper is that if you actually look at the alpha to iron ratio, so on the left here we have aluminum, on the right here we have magnesium, they're both alpha elements. You can see that the alpha to iron ratio actually did not remain high the whole time. It actually, at metallicity minus 1.5, it had a lower value and then it shot up when the disk was spinning up. So this is actually quite surprising, because traditionally we think that early on in the Milky Way we only have or it's dominated by Koch-like supernovae, right? So the alpha to iron ratio should always stay high, and then it gradually declines when the disk forms. So this is showing the contrary, is that you actually started slightly lower than the disk, and then you went up. So the purpose of my work is basically to investigate what's causing this alpha to iron rise. And it's interesting to note that this is not the only work that showed this alpha to iron increase. So Balakurov et al., they had a follow-up paper looking at the nitrogen to oxygen ratio, but they look at the globular clusters, the alpha to iron ratio for globular clusters. So on the right here, these are the average abundances for the in situ globular clusters. So they have these orbits. And we can see the same thing, right? Even for the globular clusters, it had very low alpha, and then when the disk was spinning up within this metallicity range, the alpha to iron ratio went up. And another paper that showed this was from Arisa et al., also from last year. So this paper, they actually selected stars differently. They actually look at the XP spectra from the Gaia survey. So the XP spectra are very low resolution, but they were able to extract the metallicity from the spectra. And then they showed this centrally concentrated metal pool population in the Milky Way. And then they cross-matched this population with apogee to get the alpha to iron ratio, and basically plotted the alpha to iron ratio for as a function of eccentricity in orbits. So you can see on the left here, even though we restricted the stars to eccentricity less than 0.2, so these have very circular orbits. You can still see this trend, right? It went, the alpha to iron ratio started high, it went down, and it briefly went up, and then it joined the high alpha disk that we normally know. So it's quite interesting, right? So, but the really interesting part is that from the metallicity distribution function here, Rhys et al., they show this constant slope in the metallicity distribution function. And they derive this formula to basically investigate what's causing this slope here. And essentially, you can see that right here, this term needs to be equal to 1. And for that term to be equal to 1, the two terms in the brackets need. you can have very, very little stellar mass. So here the M star versus mg. So M star needs to be very, very small. Or on the right here, the tau is the star formation timescale. So the longer the timescale, the less efficient the star formation is. So for this term to be 0, then your star formation needs to be very, very efficient, very short timescale. Or your m dot g, which is the gas accretion rate, needs to be very, very low. So it's quite interesting they derived it just from this constant slope in the MDF. So another paper that showed this and investigated this is from Conrad et al. 2022. So this is actually using a different data set. This is the H3 data set. And they show that they also had this similar alpha to iron increase. And they ran a chemical evolution model to try to explain this. And they found that if you increase the star formation efficiency by a factor of 25, assuming you have enough gas in the model, you could explain this. So that's interesting. You can ask later why my conclusion is different from theirs. So that's a question you can ask later. But for now, we'll push on. So let's just look at the theory. So the first is what produces alpha elements. So if you look at here, I showed it already for magnesium, mostly from massive stars. Then the question is, how do we have more evolving massive stars? You could change the IMF, but there's too much variation in terms of the IMF. So I think we prefer to just boost star formation. Then the question is, how do we boost star formation? We could increase the star formation efficiency, or we can add more gas, or both, right? Because the more gas you have, the higher star formation efficiency, the higher star formation rate is.
Yes, but doesn't Fe go up as well?
Yes, it will go up as well.
So are you trying to, okay.
So why I'll talk about it very soon. Yeah, so yeah, Fe is also very important. Yeah. Yeah, so there's one caveat here is that if you just increase star formation efficiency, you need to maintain the gas reservoir. So we have enough gas to actually support the increase in star formation rate, right? Otherwise, you run out of gas, you just don't form any stars. So most likely it's a combination of both, but we think that if you just increase star formation efficiency, you should also increase the gas inflow rates. Okay, so now we're going to design an experiment to actually replicate this with my model, right? So we're going to divide the proto Milky Way into sort of two phases. The first phase is the proto Milky Way that's going to last for 1 gigayear. And then when the proto Milky Way reaches that timestamp, we're going to either allow it to change the star formation efficiency or gas inflow rate, or both, right? You can do whatever you want, go wild. And then we're going to say the Milky Way is spinning up and this is forming, and we're going to give you 800 million years to see what happens, right? Can the alpha to iron ratio really go up? And if it does go up, what do the parameters actually look like? So this is what you mentioned. So we need to define the alpha to iron increase quantitatively. So we have 3 key abundance ratios here, of course, to go with the scenario we have here. So the iron abundance needs to reach minus 1.3 after 1 gigayear, so the end of the proto Milky Way phase. And then the magnesium to iron ratio needs to drop to 0.25 from the maximum dictated by the core class supernovae use after 1 gigayear. And then after the entire experiment is over, after 1.8 gigayear, the magnesium to iron ratio needs to go back up to 0.31 to meet the high alpha disk in the Milky Way. Yeah. So yeah, so these are the parameters we pick. So the top here, we have the fixed parameters. So these are just picked from literature values that people have used to study the Milky Way. And the bottom here, we have 5 free parameters to explore what the conditions of the proto Milky Way are like. So you can see we have star formation efficiency that covers a wide range, is factor of hundreds. We have the initial amount of cold gas, so that will jumpstart the model. We have, of course, the gas inflow rate. We have the cooling time scale of the warm gas. So the longer it takes for the warm gas to cool, the longer it takes for the gas to come back, for the metal to come back and reach the local ISM. And of course, we also have the fraction of white dwarfs from the progenitor stars. So that determines how much iron is going to be released from the same amount of star formation. Yeah, just to emphasize, the star formation efficiency and inflow rate can freely change within our parameter range. So you can jump from 0 to 5 and for the inflow rate and for the star formation efficiency you can change quite significantly. Yep, so we run an experiment, we'll run a model for 250,000 times, 500,000 times until we have a sample of tracks that we can select from based on our criterion. So you can see here on the top, I'm just applying the criteria on the metallicity. So all these tracks, we have to reach that metallicity after 1 gigayear. And middle here, I'm enforcing the criterion on the alpha to iron ratio. I can see there's a concentration of tracks here. And then I'm forcing the last criterion, so the alpha to iron ratio needs to go up. I can see that all the tracks that are remaining, the alpha to iron ratio went up. Interestingly, even though I did not force the metallicity of the model at the last time step, almost all of them had a pretty high metallicity, -1 or beyond. So that's interesting. So what are the results like? What do the results actually tell us about the cause behind the alpha to iron increase? So this is showing the change in the star formation efficiency and the inflow rate. So on the left here, you can see roughly 60% of the model actually had a decrease in star formation efficiency, and 40% had an increase in star formation efficiency. So it's roughly 50-50, right? The star formation efficiency can go up or go down. It doesn't seem to have a strong effect on the alpha to iron increase. But you actually look at the inflow rate, it's quite shocking that 100% of the model had an increase in inflow rate. So apparently, according to my model, the increase in inflow rate is very significant for the alpha to iron increase. So we can interpret that as the alpha to iron rise, a signature of accretion. Gas accretion.
Different composition gas, then, I guess. So the stuff that's coming in.
Yeah, the stuff coming. Yeah, so the stuff coming in is different. So for the first 1 gigayear, all the gas is coming in pristine. And after the first gigayear, we're going to have very metal poor gas, so with metallicity -1.5. So the pristine, but it's still metal poor, so it doesn't contain a lot of metal to influence the composition that much.
And what's the alpha over Fe of incoming gas?
We set it to be relatively high. So there's some alpha, but it's metal poor enough that it doesn't have a huge impact on the composition. Yeah, great question. Yeah, so just a caveat here. So earlier I showed the work by Charlie Conrad et al. 2022, and they show that the increase in star formation efficiency is very crucial. And I think that's because they actually adopted a very, very low star formation efficiency to begin with. So you can see here in my model on the x-axis here, this is the original star formation efficiency during the initial 1 gigayear. And the y-axis here shows the ratio between the new star formation efficiency and the old star formation efficiency. So you can see that when your initial star formation efficiency is very, very low, the star formation efficiency can only go up, right? So this is a function of regional star formation efficiency. So I'm interested to know whether you can see the sort of condition from simulated galaxies, right? Do simulated galaxies have very, very low star formation efficiency to begin with? If that's the case, then the increase in star formation efficiency is necessary. But say we can adopt a higher star formation efficiency for simulated Milky Way analogs, then maybe that's not the case.
Can really change the star formation efficiency?
Reason is hard to do it. Yeah, so the interpretation from the original Conrad 2022 paper, they think that if you look at simulations, right, when the disk forms, solar gas compressed, so the star formation efficiency can go up to like 5 to 10 times in simulated galaxies. So just the formation of this can increase star formation efficiency. Yeah. Does it make sense? Any questions before we jump into the next section? Okay. Okay, so now that we investigated the proto Milky Way, we can now look at the disk of the Milky Way. And one of the prominent features of this, the Milky Way, is the bimodal alpha to iron distribution, which I'll explain a little bit here. So here, this is just a simple model of the diagram of the Milky Way. So if you actually look at the disk and you plot the stars in this 2D plane, so iron versus alpha to iron, you can see that there are actually two populations in the disk. There is a concentration of high alpha stars that are roughly 20% of them, and then you have 80% of them, they are low alpha stars. And if you plot them, it's not very clear here, but normally in apogee data, you can see a very clear gap between these two populations. So this is rather interesting feature of the Milky Way, and people have been coming up with theories on how to explain this. The more interesting thing is because the Milky this variation of high alpha versus low alpha as a function of location of the disk. So here, from left to right, we're going from the central region, 3 kiloparsec from the galactic center, all the way out to 15 kiloparsec from the galactic center. And then from bottom to up, we're just plotting the absolute height from the galactic plane. So you can see we have 500 parsec, 1 kiloparsec, and 2 kiloparsec. So you can see here, there's quite a lot of variations, right? So let me just help you a little bit by focusing on the outer region first, right? So if you look at the outer region, all you see is low alpha. And people interpret this as a sign as the thin disk flaring when it goes beyond the solar neighborhood. Because the thin disk flares, all the low alpha stars are going up to high Z regions. So it doesn't matter which Z zone you're looking at, you only see low alpha stars. So that's not very exciting. And there's a similar story if you look at the low Z region, right? Because the low Z region is in the disk, and that is the thin disk. We have a lot of low alpha stars. They form later on when the alpha to iron ratio has already dropped. So if you look at the disk, you only see low alpha stars. The interesting part is that when you look at the inner regions, at intermediate Z regions, then you see this wide variety in the very density, right? So you can look at so we look at the Z from 500 parsec to 1 kiloparsec. You can see in the inner zones, we have more dominant high alpha population. And then when we move towards the solar neighborhood, we have this very prominent bimodal behavior here. And then as we move away, the low alpha takes over again. And if you look at the very high Z regions, we can see the high alpha population can dominate all the way out to 9 kiloparsec. And then the low alpha region, low alpha stars dominate again. Right, so this is the region that's actually show the most variation in the density as the most interesting region. So just a summary, high alpha is more pronounced in inner region and high Z, and then the alpha to iron bimodality is the most pronounced in the solar neighborhoods. Another interesting thing here is the chemical abundances of these stars actually correlate with kinematics. So here, the color is the eccentricity of the orbits. So you can see here for the high alpha stars, the eccentricity is actually higher than the low alpha stars. So you could come up with this scenario, right? So maybe the high alpha stars they were not born in the solar neighborhood because they have such high eccentricity. They could be born in the inner regions and then migrated to the solar neighborhood, right? So this, if you mix these two populations together, one from the inner region and one from the solar neighborhood, you get this bimodality. There's one theory for explaining the alpha bimodality. There are many theories from simulations. I'm just going to introduce a few here. These images are actually generated by AI, so apologies if they're not very representative. Clumps, and these clumps fall in, and you get this high alpha population. Another one is that you can have a gas-rich merger. Again, we have this galaxy here. You have a lot of gas coming in early on when the high alpha stars is still forming, and this huge amount of gas will help you form more high alpha stars. Therefore, you have this alpha bimodality. And another one is quenching. So that I told AI to generate a bar galaxy on the right, but it doesn't look very good. So apologies about that. Again, so when the bar forms, the gas surrounding the bar can be funneled towards the inner regions. So for the solar neighborhood, that can create a depletion of gas that causes the star formation rate to quench during the intermediate alpha regime. So that can give you the gap between the high alpha and low alpha. So these are the four major theories from simulation. So I have a summary of all the simulation works you can check later on, showing all these different scenarios. But for my work, I'm just going to focus on the scenario with radial migration. I'm going to create a vanilla boring galaxy. I'm going to have radial migration and see if we can generate the alpha bimodality. So we remember this model we had earlier, which is one zone. We're taking the entire galaxy and treat it as one box. But now we have radial zones, right? So we basically copy and paste multiple times. Then you have each box represents different radial zone of the Milky Way. It goes from the inner region all the way to 20 kiloparsec out from the galactic center. And within each zone, you have all these processes happening. And to transform from a one-box model to a multi-zone model, you need to take into account the exchange of stars and gas between different zones. So that's why I mentioned earlier we have radial transfer of gas from the outer zone all the way inwards. And also because we have radial migration of stars and gas, so stars and gas naturally get scattered over time to surrounding regions. So because this is a multi-zone model and we're studying the distant Milky Way, we have a wealth of information we can draw the parameters from. So these are just the parameters we are using for this model. Yeah, so quite a lot of parameters. So one feature from our Milky Way, from our simulated Milky Way here, is that we have very, very boring star formation history, right? Because we want to create this vanilla baseline Milky Way model. So you can see here, this is a star formation history for our galaxy. And essentially for the last 10 years, the star formation history is flat, right? So you can already see here, then you cannot have late accretion or quenching events, right? So the bar formed sometime like 8 gigayears ago, so you couldn't have a quenching here because star formation rate here is flat. You also couldn't have like a major accretion to feed the gas reservoir or bring high alpha stars, basically. So can we make it? So again, this is just an updated plot of the same distribution from the apogee data. So you can see the most interesting regions are the inner zones and intermediate Z, right? So if you go to high Z, all you see are high alpha stars, but at the intermediate Z here, you can see the relative density between the high alpha and low alpha changes quite a lot. So here are our results. So you can see, again, at very, very high Z, just high alpha stars, that's expected. But if you look at the intermediate Z region here, we start to have low alpha stars here. And if you look at this row here, you can see we have this alpha bimodality that's reproduced that we also see in data. So it reproduces the alpha bimodality as a function of location in the disk qualitatively well. Yeah. Now, because this is a chemical evolution model, we know all the stars, we know where they form, we know where they end up, and we know exactly what the chemical abundances are. So we have a lot of byproducts from this model. So if you're interested in looking into the chemical property of the Milky Way or age distribution of the Milky Way, we have a lot of byproducts here. I'm just going to show a few here. So the first thing here is that we have the age melody relations, or more generally, the age abundance relations for all these stars at different regions of the Milky Way. Another thing is we can also have the stellar abundance distribution. So here I'm just showing the alpha to iron distribution here. Also, because the models can vary, we have a suite of different models here investigating different scenarios of the Milky Way. So the distribution, of course, can change quite a lot depending on our assumptions. And we can also have very detailed age distribution, right? So what I'm showing here is just a age distribution as a function of abundances and location in the disk. So if you're interested in getting the ages for your stars, you can do that from the model. And for the remaining 5 minutes, I'll talk about some future applications for this model. So the first application here is the GACO survey. So this is a survey that targets 30 nearby galaxies. So it's going to have spatially resolved chemical abundances in these galaxies. So we can actually adopt my multi-zone model to actually fit the chemical distribution of these galaxies and see if we can infer the physical conditions of these galaxies. So half the galaxies actually have a bar and the other half, so they have a wide range of morphologies in these galaxies. Another application I'm working on right now is the chemical distribution of M31. So this is from a very recent paper, David Niederber, 2023. So he actually used the James Webb Telescope to look at stars in M31 galaxy. And you can see here, there's no bimodality in alpha. So this is actually quite surprising because I think that because M31 is a disk galaxy, is quite massive. So people think that we should expect alpha bimodality from the galaxy, but apparently from existing data, we don't quite see it. However, if you look at the planetary nebula from a recent study, you can see this wide range of chemistry from M31. So maybe we're not observing the right region. Maybe we need to have more data on M31. We don't know yet, but I guess I can explore with my model. And just have some the conclusion slide here. So chemical evolution models are very cost efficient to investigate the physical properties of galaxies. So for reference, for the one-zone model, if you want to run a model for 13 gig a year, it only takes like 20 seconds. That's why we can run the model for hundreds of thousands of times. And for the multi-zone model with everything turned on, it takes about 30 minutes, right? Compared to hydrodynamical simulation is a fraction of the time. And you can get the detailed chemical distribution here. The formation, the spinning of the disk coincides with the increase in gas accretion, signified by the rise in alpha to iron ratio. So if you observe maybe stellar groups in the Milky Way, so people actually have found a group of stars in the Milky Way connecting the proto-Milky Way to the high alpha disk, and it had this signature of high increasing alpha to iron. So that could be the group we're looking for here. But if you see that in other galaxies in the future, that could be a clear signature of accretion. And then we have the alpha to iron bimodality as a function of functional location in the Milky Way disk. It can be explained by just a simple model with boring star formation history when the effect of radial migration is included, right? So it means that the Milky Way is probably more boring than we think. It's probably not very special, and we should expect to see the alpha bimodality in more galaxies in the future. And lastly, hope to extend the application of chemical evolution models to more detailed information about the Milky Way or other galaxies in the future. And this is all I have, and I'll take your questions. Thank you for your attention.